It's a great pleasure to have today for our fifth distinguished lecture, MARVEL lecture, Dr. Pierre Villars from Materials Phases Data System. Pierre, if I may, got his PhD in 1981 at the Institute of Crystallography at ETH, where he had also a master before and a bachelor in Winterthur. In his academic career, he was a research professor at the University of Waterloo and in Ottawa, the National Research Council in Canada. But also, I mean, he's extremely well known in our community as being the co-editor and the copyright owner of the Pauling file that I hope we'll hear about. Is one of the fundamental tools in our field. He's been the founder of Materials Phases Data System. And I think he has edited or co-edited an impressive 23 volumes of crystallographic data text. And while chatting here, he just mentioned a sort of Eric Wimmer that many of you will know from his activities with materials design. Is a longtime friend, and Pierre told him 25 years ago that he needed a database system for his material simulations. And so hopefully we are finally getting there, so we all look forward to hearing your talk and your vision about this. Okay. Thanks again for the
Thank you very much, Nicola, for introducing me, and also thank you much for the invitation. That is for me, of course, a pleasure to have the chance to tell you a little about my ideas in context with MARVEL. I think it is pretty obvious that the trend coming from Materials Genome to over the Japanese with Materials Informatics, and now also MARVEL, but also the Chinese start really programmed to make heavy calculations, modeling, or simulations in material science. Now, here I just highlighted in yellow when I was reading a little about them, what attracts me most, and I will talk about that in my presentation. The major aim of my presentation is to draw a roadmap by taking advantage of different data mining techniques using a huge materials database, mainly from experimental data published in the world literature, and try to come up with a practical way how to find ways to make high throughput quantum simulations. In that context, I think the idea of the five paradigm of science and its impact to MARVEL. In 2009, Jim Gray introduced the fourth paradigm, and what he said, it's pretty simple, but it was in a very general level, not only for material science, as a general in science. He said, okay, several thousand years ago, we started already humanity to measure, and that he called first paradigm. Then several hundred years ago, one started with the theoretical. And the last few decades, simulation was coming up. Now, as a man from Microsoft, he said, okay, the logical is you combine it, and as a consequence, you get an eScience, that means data-intensive scientific discovery through data exploration on a very general scale. Now, when you look what he said in the area of material science, we ask us first, is it possible or not? Then you have to say, what happens, what happens is data are in general published in e-journals or e-books, or formally in publication, which are friendly for human beings to read it, but are not so friendly for computer. So what you need, or what we did our activity in the last 35 years, is trying to put this information from original publications in a relational database, which is open-ended, and which it also has adding to it a critical evaluation point. And when you look from Jim Gray, in principle, this covers roughly these three first paradigms. Now when I look at MARVEL or also at the American approach, in principle what you try to do or are going to do is you will organize or calculate data and create a database from simulated data. Now what the fourth paradigm says is you should link it, and when you link, then you can make data exploration, also in the sense of data mining, as an example. But when you look now presently, you have no real link that you can do it properly. So, and I just call that approach MARVEL. You could call it differently, and that I call it, it's one example polling file. In my presentation, I like to give, first I like to ask two questions, and I hope I can give you the answer in that presentation. The first question is, okay, when you cannot really in material science apply this fourth paradigm, what do you have to do that you could apply it? And the second key question is, now definitely in any kind of approach, when you like to make high throughput quantum simulations, you need a clear focus, because you cannot make infinite many calculations. Where to start? What are the guidelines? That you really then can try to apply that. Now, in my title, it is written that first I come to the three pre-requirements when you like to link different databases, materials produced by different groups worldwide, and also if you like to link different group of data like crystallographic data, phase diagram data, or any kind of physical property data. Always, of course, restraints to mainly single-phase samples or properties. A key point is definitely, and without that it is not possible, you need to introduce a properly, perfectly done, in bracket, prototype classification. The idea is very old. It was introduced by Bill Pearson together with Strukturbericht 60 years ago. And then Professor Patti and his group developed first time the program structure tidy, which made it possible to standardize the published data completely, that you can really compare different determination or to find out if the compounds are isostructural or not. Without having this as a foundation, I think any kind of link will not really properly work. The second requirement is you have to introduce, we call it distinct phases concept. It's very simple in practice. To realize it's a little more difficult. You look for every system which we have information from the world literature. You look how many phases there exist, and that you can distinguish in that you have with the fully standardized, you know which prototype. Here as an example, this compound crystallizes in cesium chloride, CP2, Pearson symbol, and that's the space group number. But with this name, which are unique, defined and built up as a distinct phases database, and every entry and information you find, you link to one of those, then you can link it. The third requirement, that's most likely the most heavy one, it is you need a database structure which is open-ended, includes any kind of materials data, always on single-phase pronouncements, not multi-phase samples. That's the next step. That you can link different kinds of data so that you have a structure for the structure data, you have a structure relational database for any kind of physical property, and also for phase diagrams. That are the major fields in material science. Here it is important, and I think that is also in context with MARVEL. You can make any kind of simulations, but I think it is it's highly recommended that you have a reference database where you compare your results with the published data from the last 100 years, which are critically evaluated in these 4 fields areas I mentioned before. Now, to be realistic, there exists 2 databases in the world which are kind of comprehensive. It is Landholt-Bernstein and the polling file. We have a collaboration with Landholt-Bernstein, and the weak point on Landholt-Bernstein is it is not in a relational database. It is a highly indexed book, which makes it actually at the moment impossible that you could really make data mining in a professional way. But of course you have plenty of data. Now, I like to introduce the 5th paradigm. Now, I explained here before, when you had the picture from Tim Gray, that when you like to be able to combine experimental data from the world literature with calculated from simulation, and you have introduced these 3, then in principle you can really start to link them by computer systematically as reference, but also as starting point for calculations. Now, certainly if that is once realized, then in principle any kind of database producer which follows the same criteria can also be linked worldwide, and the same like also here any kind of calculated or simulated product, like also Materials Genome could be in principle be linked without fundamental. Of course you will always have a lot of work, but in principle it will work. Now, the 5th paradigm is something which we added together with Shuichi Iwata and myself. The point is, when you like to build up such a kind of database, and that was also a lot of discussion with Eric Wimmer about that, then of course you cannot calculate everything. You have to start something, and you are looking from the infinite many possibilities you principally could calculate to find restraints to focus on the most interesting or most probable combinations or compounds or compositions. Now, to the first question, I think I can give you the answer. It is possible, but you have to introduce prototype classification, distinct phases concept, database, system, and open-ended. And one example is, which is very robust, as the polling file is now 20 years plus, and it worked for almost all cases from what is published, what we in principle include. Now, some words about the polling file. I will make it relatively short because I could talk about hours, because that's actually what I'm doing, or we do, for the last 35 years. This project was started in 1994 with a collaboration by GST, is a Japan Science and Technology Agency, and my company. And the intention was to build up an inorganic materials database and design system. By the way, I got permission from Linus Pauling to use his name. I'm not misusing his name. I got the permission. Here are the names of the major leaders. And now, already 22 years ago, we had what was the major, why did I get funding from the Japanese government? Not only because of collecting data, because that is in general called kind of slavery work, not so scientific, but it's a requirement. And it's very interesting as a matter of fact. But it is in principle what also MARVEL is going that direction. You want to be able to design, find new novel materials with predefined properties. Now, in principle, already 22 years ago, you had 2 extremes. You could use any kind of data mining technique by using published data, mainly experimental data, and find pattern like polling did in older days. The bottleneck was very clearly, and at that time, no relational database. So it's pretty quickly over the game. And that was one of the main. And the other one is, of course, at that time already, it started to become significant. And that was also in the beginning where I had discussion with Eric Wimmer. The difficult point is that one, which still stays. And that was the reason why we thought you need a reference database. Now going to the next. What did we do the last 25 years in very short? It was, we used about 25 million Swiss francs, and this was converted in about 500 manpower years editor work. And this edit team created a processed 150,000 publication from the world literature, starting from 19 till now. We created roughly 290,000 crystal structure entries, 42,000 phase diagram, fully standardized, colored as vector plot, retraced, critically evaluated, and about 250,000 physical property units. Now, from this funding to survive, almost half of the funding were recuperated by products which are in the market, and it might be that you used some of the products which contained LPF data, but which you not even knew. I'll just list here shortly. We have 10 products they are distributed by different publishers. One is the Atom work, which is published by the National Institute of Material Science in Japan, Tsukuba. Then one binary edition, a smaller offline. Then Pearson's Crystal Data and Alloy Phase Diagram Center, published by ASM International. That is online. Then a relatively large, that's now I think the largest database in that area. It's Springer Materials. And this is a combination between Landholt Bernstein on the merge and LPF. But as they are flat, we had to make our flat. That's part of the game. Not very scientific, but you survive in that way, not in another way. And then 2 hard copy products. And then what most people don't realize is the known powder pattern file from Philadelphia. All calculated powder patterns, in a sense, use our coordinates. And then finally, also 11 volumes from LB series about crystal structures. So everywhere the data, that is, it's the master database, and we select certain data and create products. Now, this is very fundamental and important, and for any kind of database producer, also for you, when you make calculations. Very simple. For any kind of data mining technique, that is valid. If you like to find patterns in not evaluated data, it's garbage in, garbage out. You will not succeed. And I think that's a very important point. Now, also a point which most people which are not experienced in databases, especially when you take it from the literature, the data have to be critically evaluated and as much as possible standardized. And this has to be done not by students, it has to be done by full-time people which devote their time to become specialists and do it properly. I will not mention too much, but just to show in the LPF, the structure part, we have over 50 different modules to check about 100 different things on 5 different levels. One is in the input level, but in the editor level already. Then you also start in the consultant level that you make calculation, the interatomic distances, check if the symmetry is consistent with the data which are published. Also going really making powder pattern calculation and compare it. So really going in it. And finally, roughly spoken, 5% of the data have heavy mistakes. And we try to correct it, of course always giving comment, and about 10-15% have comments with something added by the editor. Now to the next. data mining by using elemental property parameter, which goes, of course, not simulation, but I will show you in which direction I like to point. Now, I think for simulation people, the next question is pretty straightforward, but I will highlight a little some details. Both, if you go from the quantum simulation way or from the data mining way, which is data mining, I mean from the published literature worldwide, you start in principle always, you have the periodic table, and then you start with selection of the element, possible combinations, then their concentration, and then finally pressure, and so on. No one can go around that, but that has consequences. In data mining, I show two very extreme cases. One extreme, you search for pattern within data, where you lose the connection to the periodic table, where you lose the connection to the constituent chemical element. And I take always as example Fleischer's plot. He found in the literature, or measured, I don't know, for 70 compounds plus minus, the density and the melting point. And then he also, with color, he indicated which prototype. He was interested in having low weight, high melting material. Also he knows he should have such a structure. And for his problem was very efficient because he got some information. But of course, he has first to have found these 70 compounds or additional ones that it helps him. He cannot make a connection. Now, the next one, the striking, that actually guided my research work for 35 years. That was Miedema. He published the first time in 1985 a striking, for me, very striking result. He did it in a quantitative level, a materials property with its constituent chemical elemental property parameter. He took a very simple question. He said, I'll focus only on binary phase diagram, and a diagram or a system is compound forming when it has at least one binary compound. Then it's delta half formation negative. This is right. And the other one are positive. And then he introduced for most chemical element a chemical potential, a fixed number. And here for the interatomic electron density, also a fixed number for most chemical. Then he found a very simple plot with a simple expression of this one and a simple expression of this one. And with about 6-7 such plots, he could separate the phase diagram in two groups, formal and non-formal. And that sounds not very interesting, non-formals. But of course, if you make calculation on non-formal system, you waste your energy. And for me, it was of course striking because as soon as you can do that, a materials property link with tabulated elemental property, then you can, for the remaining systems, you can simply calculate and you have a nice prediction. Much better than any kind of feeling. Your feelings are always wrong in comparison with such strong plot. Then, in that animated through his work, I collected all elemental property parameters which have been published worldwide in publications, about 100, where you have most of the chemical element you had values. And then I discovered that you actually, when you plot them, elemental parameter against the periodic number, then you get a nice pattern that I took here, the pseudo-potential from Zunger. You see a nice behavior along the long period and a nice behavior along each group. And what I here actually, I listed the periodic number. The periodic number is a simple counting from the chemical element. You start here and you count down and give each chemical element a number, and you go to the next group and you go from left to right. So you have at the end the atomic number and the periodic number, both integer number from the chemical element, for each chemical element. And now these four groups. In the next, I show you in very short, that is the atomic number in function of the periodic number. You see actually the periodic table in it. Now I found a few years ago a function which can quantify the size, the atomic size, as a sole function of the atomic number and the periodic number, which is amazing. And the same with the reactivity, or very often called electronegativity. And it's very strange, physicists liked always the radii, also pseudo-potential radii, and chemists like Pauling liked electronegativity. And it is funny, it is the reciprocal value of it. So from these four groups, I could deduct three of them which are sole function of AN and PN. Now coming as a conclusion to pattern recognition or data mining, we can ask the question, do we have reached a new quantitative and qualitative level of data mining as elementary property parameters are simple functions of AN and PM? Because I think to quantum simulation people, I have not to stress that you work in principle with the atomic number in the best way. And in early time, any kind of data mining were, especially when you make data mining with a few data, I mean 100,000, it's almost nothing. When you start to make pattern recognition with 10,000, 100,000, and then I don't mean data points measured on a sample, I mean then 10,000 or 100,000 compounds, then when you find then pattern, then it's not an incident. Then behind is something. And the something is, of course, this number and this number. Now, coming to the question, can we develop with the help of data mining using the polling file, mainly experimental published data, a strategic way to make calculation to which element combinations to select or which compounds to be selected to be treated first. Now, 2-3 years ago, I published a paper where I found 12 principles. And these are actually 4 different cornerstones. And in short, when the first cornerstone is, of course, given through the 100 element plus minus and its combination possibility, you have infinite many possibilities of materials. Punkt. This is, of course, for MARVEL and any kind of approach, hopeless. Too much work, even with fast computers. Now, then I tried with the aim to look at experimental data if we find restraints given by 100,000s of data sets which can make the field a little narrow down. And the first fundamental question was laws which control that control chemical element combination which do not form. Also Midemas game. Extended. The third cornerstone, there I found 4 different principles, and here also 4, is if you find laws that control the ordering of the chemical element within a crystal structure, which you look at, and try to find very general valid ones. The last one is if you find correlation between the link of the position of the chemical element within a prototype and the periodic table. Now, if that is the case, we ask our question, can we use it to develop a way to do it in a systematic way? For the first cornerstone, that means that you have infinite many possibilities. I just show you one plot. And for these numbers, I took the Springer materials. That's the most comprehensive on that level worldwide, and that represents about all chemical element we have some information. It's never complete, of course. With binary system, we have for 72%, we have information. With ternary, it goes much down, and there you see we are pretty flat. This is already a definite message. And the other message is even stronger, the number of combinations. When you have quaternary, you have over 75,000 million chemical systems to consider. That nature offers you. And each one could be a good material or a novel material. And at the top of it, the average, just at the top, in the binary you have in average 4.5 compounds. In ternary you have 4, and here you have 3 or less. But here you have too little data to really be sound. And there exists meanwhile 32,000 different prototypes in inorganics. That means nature in principle symmetrically arranges atoms to each other in 32 different different ways. Which is, I don't know, nature has a lot of fantasy. Now, because that leads in infinite. Now we try to I show you shortly for the 4 principles we found, again with the help of LPF data, and we looked at about the 1,000 most popular prototypes, and its representative, we looked about at 200,000 entries. And found the following principle: the compound formation principle, the number of chemical elements per compound restraint principle, the active composition range principle, and the stoichiometric restraint principle. For each one I give, because we have restricted time, for each one I give just one plot. This is for the binary case, but it works also for ternary and quaternary. And Ton Niesen and Miedema was working binary, and I was once 3/4 of a year in NatLab in Eindhoven, and we tried at that time with Ton Niesen to find an extension of Miedema's model to ternary, and we failed. We didn't succeed. Later I found a way. And it was, but it's too much in detail, but I show you, I showed what is done is very simple. You look at the binary system, you list here the chemical elements with increasing periodic number, and here periodic number of the element B, and then here it's the actual data you have, and you see in the gray zone you have a non-forming area. And that is also to most people surprising. When you mix 2 chemical elements with a periodic number 50 or lower, you will find no compound. And of course, when you look at the database without a plot, without a parameter, you will not see it. It's hopeless. And this has been extended by different works to ternary and quaternary, and what is very surprising, the ternary and quaternary the separation is simpler, not more complex. The most complex it is in the binary case. Now coming to the next one. In short, we looked at all compounds which have no mixed occupancy, and separated them in binary, ternary, quaternary, and looked for each point set its coordination number from all those compounds. We looked roughly at 120,000 compounds and roughly about 450,000 point sets. And made a statistic here. It's plotted the coordination number versus here, or the atomic environment, or people call it also coordination polyhedra. What do we see? Chemical elements like high coordination number, the point sets. When you go to binary and ternary, you have a large range from very small coordination number till very high. It's a very high geometrical diversity. When you go to quaternary, and quaternary in 6, you get dominantly structure where the atomic environment is 6 and lower. And what is striking, when you go from quaternary to quaternary, sexternary, you don't win anything anymore, geometrically. So you cannot expect, when you go to higher systems, you will find something fundamentally new. You will find it in quaternaries. This is, of course, for reducing the number of combination of big consequence. Now, that is also simple set. The gray zone there, our area is 5%. You need to have to form a compound at least 5% of the second, third, or fourth element. In those regions, you will never find a new compound. There you have either nothing or a solid solution, or two-phase or three-phase sample. And this is, I love this, because in my PhD work, it was a part, and I couldn't solve it at that time. I tried to solve it through space group, and looking at that space group, make all combinations and to try to reduce, but then I ended up in one space group with 20,000 possibilities, so it's hopeless. Meanwhile, we went another way around. We looked here, I plotted here 20,000 ternary compounds which have no mixed sides in a triangle. And here you have the 10 most often occurring binary stoichiometric ratio, which cover 98% of all binary compounds. And I link them from the corner to here, and 99% of all ternary compounds are lying on these 10 lines, which gives you a big restraint to the stoichiometric ratio. So, conclusion short, with this 4 principle, we bring the infinite to less than 1.8 million systems, which in principle you have to look at in first priority. Of course, you can also look to others. But I think that makes it already a kind of doable. Here I give just 2 examples, and there we watch now the ordering of the chemical element within the crystal structure, and nature is there also very, very strict. It is very flowerful and very fantasyful, but has strong restraints. One principle I show you, that is the simplicity principle. I list here a frequency plot. It's the number of compounds, and here plotted either the number of different atomic environments or coordination polyhedra per compound, or number of point sets per compound. And you see what nature likes. Nature likes structure with 2, 3, or 4 different atomic environments. It doesn't like a structure with 50 different polyhedra kinds in the structure. It doesn't realize that. The same you see indirectly also with the point sets, of course. Now the second principle is the symmetry. Already Lavas, which founded the institute where I made the PhD, said that nature likes symmetry. And it is really true. What I did here is simple. I have the frequency of all LPF entries versus the space group numbers. And you see within each crystal system, you have not statistical distribution. Space groups with a higher symmetry are strongly preferred. So, you know, nature likes simplicity and symmetry. The other 2 I jump, but I tell you what's the conclusion. We know, or I already told you, that there exist over 32,000 different prototypes. Now, with those restraints, and principally we have seen we can reduce actually to those which are most often, and to a few hundred prototypes, 500, 600, 700. And that makes it again doable, and there are in general also the simpler structure types. Here I just showed you the first 100 most frequent prototype, like this one has 6,000 compounds and goes down. When you go over 2,000 in general, you have per prototype 1 compound. And to make their prediction It's tough. I would not do it. Now the last point, I show you also here just two, but to give you the idea, I try to link the position of the chemical element in the structure with its position in the periodic table. And again, I show you here just a few examples, but I did it systematically with all 1,000 prototypes which has most representative, which represent about 80% of the whole database. Here on one example, this prototype has 4 positions and there are 23 compounds known. This position is always occupied by a P1 element. These 2 positions are occupied by a D7 element, and this one by a D1 and F11 element. Now you make the combination to come to 144, principally when you combine all those. And what is striking and also surprising, the more complex a structure is, the more the restraints are here. When you have a simple structure, then almost every combination can give much more. There the restrictions are much, much smaller, like in sodium chloride, where you have thousands of compounds. But this has also an impact when you look for a calculation that you have not to calculate infinite many possibility or all combination. You can restrict based on experimental fact as a starting point which one are most likely to occur, also having that structure type. The second is the structure map. That's an old story, and I have also published, Pettiford has also published there and several, but the principle is simple. The pattern is a little more complex, and I explain it just on the binary case, 1-to-1 compound. You list here the periodic number again of the element A, B. Then for any 1-to-1 compound known, you use a symbol for a prototype. For example, here the green one for that prototype, the red one here for that one, and you see nature is not simple, but it's not statistic. You see the periodicity from the periodic table very clearly. And at the top, assuming now you are interested in systems where you have no information, you are, I take it as an example here, then you can look in first priority to the surrounding competing structure types. And look then with calculation which one is the most stable one for those compounds where we have no experimental data. So it helps you very much to focus on your problem and focus on the most likely ones. Again, the 11 and 12 I jump, but conclusion is this helps us to reduce per prototype to consider just a restricted number of combination which is likely to have that structure type of interest on your side. And that works for almost all structure type which have, say, more than 10 compounds, and those which have only 1 compound, that of course it will not work. Now coming to question. Polling file and different data mining techniques proved to be successful to find powerful restriction. And here I have to stress, data mining is only sensible when you have large quantity. For small data quantity, I find you any kind of regularity I want. But they are in general meaningless. And one has to distinguish also when you read papers, if it is a serious pattern or not a serious pattern. As a guideline, over 10,000 different compounds or informations, then it starts to become serious. And the elemental parameter has best to be an integer number or to be as accurate as possible. Now, can we use those restraints, the whole framework, to find a way to guide a little MARVEL? Now, in short, I have summarized that what I said before with these so-called different principles. the key point I focus now a little on what are the governing factors, because you find only strong patterns or strong separations when you've have the right parameter. It is independent which kind of data mining technique. You can take neural nets, you can take any classical. When you have not the right parameter, you get nothing. And when you have the right parameter, you can take neural networks, you can kind of classical, you always get that separation. Just then you can fight which one is the better. But it is good. But then you touch something. So when we look at this non-forming business, which is actually deciding? It is the periodic number. You can also see it a combination of AN and PN, looking at the reactivity or the size. Then also the correlation of the stoichiometric ratio and this correlation here. When you look the ordering within a structure of the chemical element, then it is very strongly controlled to simplicity, symmetry, and the atomic environment, coordination polyhedra, which are realized in that structure. Nature has strong preferences, also for certain element combinations. And finally now linking the position of the elements in the structure and the periodic table, it is these two correlations. Now, in short, what I already said, you need to find those. If you start with the wrong, or you will not succeed. So you decide from the beginning on the final result. Of course, you don't know it ahead. That's the bad part. Now, coming to, and I think after what I said, I think it makes in a way sense that both approaches are complementary. Because why not taking profit from a huge amount of data from 100 years experimental work? In a relational database, of course. Otherwise, you have to work. I go here not in detail, but I say, okay, you have here MARVEL, you have here a database. You could also take another database, also Landau-Bernstein in principle. And then say, when you like to build up a calculated database, a simulated database, then how shall I go on? Assuming I'm not just focusing on semiconductors, then of course the decision is made. But when you say broader, I like to have an approach where in principle I could in principle treat any kind of interesting distinct group of property or family of structures. Then obviously it is focus on unary to quaternary. You don't need to go to higher system. The probability that you will find there something exotic new is very small. And most of them are actually the 5, 6, 7, and 8 have very many mixed sites, which is actually then a solid solution of a lower system. Then next, of course, that makes, in my opinion, very much common sense. Midam always stressed it very highly. It makes no sense to focus on a non-forming system when you know that in case you are looking for a new compound. And then it goes with the list on. And finally, of course, when you have built up a system where you make for a specific group of compounds, you make calculations, then take as a starting point or as a reference the existing data and look what's the accuracy level or trust level. And if you've done that systematically, then you can of course go and extend and calculate data or structures where no experimental information is, and put it in such general pictures to the experimental data and look how they fit. I think with that's the last one. How I'm doing with the time?
50 minutes.
Okay, that's not too bad. Good. Now, that's the last point. Does it make sense using the fifth paradigm, and does it make sense to link? I take now MARVEL and polling, but you can also take an own database or another database. Because what everyone is of course confronted, it is from R&D, you get raw data. And I would not recommend to do any kind of pattern recognition or starting from there. You need peer-reviewed data, except you can't. With MARVEL, and then you are in control of what you're doing, but from the published data, not. Then it at least is peer-reviewed, and then use databases which did put it systematically in a relational database, of course, hopefully in a clever database structure. Then having the similar links or having the possibility to link those and always go dynamically back and forward. And then that point, the fifth is finding governing factors. That means then I just said that would be the pool of data you have worldwide. Then the blue one are known, the other one are unknown. And then you try to find any kind of really serious pattern and go back and you improve steadily. And with time, the blue will become green. No, opposite. The green will become blue. And that's about, with that I like to close.
Thank you very much.